Hello, 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 everyone out there. Rob, Tom, nice to have you all on the show.
Yeah, thanks for having us.
Yeah, you bet. If you're out there watching the live stream, please put some comments and we'll try to make that part of the show. If you're watching later, thanks for watching. All right, let's kick this off, guys. Rob, Tom, welcome to Talk Python to Me.
Thank you.
It's good to have you both here. We get to combine a bunch of fun topics and important topics: data science, Python, the cloud, big data, as in physically lots of data to deal with, and then also climate change and being proactive about studying that, trying to make predictions and do science on huge amounts of data.
For sure. Looking forward to it.
Yeah, this will be fun.
Yeah, absolutely. Before we get into those, let's just start real quickly. How did you two get into programming in Python? Rob, start with you.
Yeah, sure. So I been a developer for, I don't know, let's say 14 years. I started at a shop that was doing Sybase Power Builder. And
that goes back a ways.
That's back a ways. And I come from a math background, so I didn't know a lot about programming, and started using Python just sort of like on the side to parse some bank statements and do some personal stuff. And started actually like integrating some of our source control at the company with Python, and had to write some C extensions. So got into the Python source code and started reading that code and being like, oh, this is how programming should work. Like, this is really good code. And that year went to my first PyCon. It was just like all in. I need to get a different job where I'm not doing Power Builder. And really, I kind of credit Python and the code base and setting me on a better development path for sure.
Oh, that's super cool. PyCon's a fun experience, isn't it?
Oh yeah.
Yeah, it's like my geek holiday, but sadly, the geek holiday has been canceled the last 2 years.
Oh no.
Yeah.
Yeah. Tom, how about you?
Kind of similar to a lot of your guests, I think. Was in grad school and had to pick up programming for research and simulations. This was for economics. They started us on MATLAB and Fortran, which I think goes back maybe further. Don't know, almost as far as you can go. Anyway, I didn't really care for MATLAB, so moved over to Python pretty quickly, and then just started enjoying the data analysis side more than the research side, and got into like the whole open source ecosystem around pandas and stats models and econometrics library. So started contributing to open source, dropped out, got a job in data science stuff, and then moved on to Anaconda, where I worked on open source libraries like pandas and Dask for a few years.
In a weird turn of coincidence, I was just the previous episode with Stan Sievert, who you worked with over there, right, at Anaconda.
Yeah. So he's the director of community innovation, and then so it was a great place to work at. Really enjoyed it, and then came onto this team at Microsoft almost a year ago now, working on the Planetary Computer.
Yeah, cool. Well, the Planetary Computer stuff sounds super neat. You get to play with all the high-end computers and the big data and whatnot, right?
Yeah, it's a lot of fun. Although I did have a chance to play on, I think it was Summit, which is one of our nation's supercomputers at my last job. So that was a lot of fun too.
Okay, well, it's hard to beat that, right? That's one of the ones that's like takes up a whole room, a huge room. That's definitely pretty fantastic.
Yeah.
Awesome. All right. Well, what are you two doing today? You're both on the Planetary Computer project. You're working at Microsoft? What are you doing there?
Yeah, so we're on a pretty small team that's building out Planetary Computer, which really is sort of three components, which is a data catalog, hosting a lot, petabytes and petabytes of data, openly licensed satellite imagery and other data sets on Azure's blob storage. We're building APIs and running API services that ETL the data, encode metadata according to the stack specification, which we can get into later, about those data sets, putting them into a Postgres database, and then building API services on top of that. That's a lot of what I do, is manage the the ETL pipelines and the APIs, and then expose that data to users, environmental data scientists, and really anybody. It's just publicly accessible. And yeah, that's sort of my side. And then there's a compute platform, which Tom can talk about.
Yeah, so all this is in service of environmental sustainability, and so we have our primary users are like people who know how to code, mostly in Python, but they're not developers, and so we don't want them having to worry about things like Kubernetes or whatever to set up a distributed compute cluster. So that's where kind of this hub comes in. It's a place where users can go, log in, get a nice, convenient computing platform built on top of Jupyterlab and Dask, where they can scale out to these really large workflows to do whatever analysis they need, produce whatever derived data sets they need for them to pass along to their decision makers in environmental sustainability.
Yeah, that's super cool, the platform y'all are building. People who might have some Python skills, some data science skills, but not necessarily high-end cloud programming, right? With handling lots of data, setting up clusters, all those kinds of things. You just push a button, end up in a notebook. The notebook is nearby petabytes of data, right?
Right, exactly. So we'll talk a lot about like cloud native computing or data analysis. And so really what that means is just putting the compute as close to the data as possible. So in the same Azure region.
So you just need a big hard drive.
Really, really, really big hard
That's drive. What the cloud is. It's one big hard drive.
Exactly. It is. Yeah. So super neat. Before we get into it though, let's just maybe talk real briefly about, Microsoft and the environment. This obviously is an initiative you all are putting together to help climate scientists study the climate and whatnot. But I was really excited to see last year that you all announced that Microsoft will be carbon negative by 2030.
Yeah, for sure. I mean, Microsoft, and prior to me joining Microsoft, I didn't know any of this, but Microsoft's been on the forefront of corporate efforts in environmental sustainability for a long time. And there's been an internal carbon tax that we place on business groups that where there's actual payments made based on how much carbon emission each business group creates, and that's been used to fund the environmental sustainability team and all these efforts, and that sort of culminated into these 4 focus areas and commitments that were announced in 2020. So carbon's a big one, not just carbon negative by 2030, but by 2050, actually having removed more carbon than Microsoft has ever produced since its inception. And that's over scope 1, scope 2, and scope 3, which means accounting for, downstream and upstream providers. And then there's a couple more focus areas around waste. So by 2030, achieving zero waste, and around water, becoming water positive, and ensuring accessibility to clean drinking and sanitation water for more than 1.5 million people. There's an ecosystem element too. By 2025, protecting more land than we use. And then also creating a planetary computer, which is really using Azure's resources in the effort to model, monitor, and ultimately manage Earth's natural systems. And yeah, so that's awesome.
That's the part you all come in, right?
Yeah, exactly. The planetary computer's in that ecosystem commitment, and that's what we're working towards.
Yeah, very cool. The removing all the historical carbon, I think, is pretty fantastic, and being carbon negative, right? So much stuff runs on Azure and on these couple of large clouds that actually is a statement about a large portion of the data center usage as well.
For sure.
How many data centers does Azure have? Like 3 or 4, right?
I think it's the most. I think it's the most out of any of them.
It's a lot, right? It's over 50 or something like that. Large data centers. I don't remember, but it's a big number
all the time too.
Yeah. It's like constant. So that's a big deal. Super cool. All right. Well, let's talk about this planetary computer. You told us a little bit about the motivation there, and it's made up of 3 parts, right?
Yep.
All right,
Yeah,
yeah. So
like it
tell us
says
about
here.
it.
Yeah, so there's technically 4 parts, because really, we recognize that technology for technology's sake is just kind of spinning your wheels, right? We have to be building all this data, all this data access, the analytics platform towards applying data and insights to actually making an impact on environmental sustainability concerns. And that's done not by us, an engineering team, like kind of, trying to figure out the climate scientists, right? We're engaging with organizations to build out applications specifically on these data and services, and partnering with organizations that have specific goals. So there's an applications pillar to the planetary computer, but from an engineering standpoint, we're mostly focused on the data catalog, the APIs, and the hub that we had touched on briefly.
Yeah, yeah. And then the applications is what the partners and other people building on top of it are really doing, right?
Exactly, and we participate in that, and help bring different organizations together to build out the applications, and use the money that we have to actually fund applications that are specifically aimed at different use cases.
Yeah, yeah, very cool. So there are some other things that are somewhat like this, right? Like Google Earth Engine and AWS, and you probably could just grab this yourself. You want to do a compare and contrast for us?
Sure.
Either of you?
Yeah. So Google Earth Engine is sort of the bar that's set as far as using cloud compute resources for Earth science, and it's an amazing platform that's been around for a long time, and is really just like a giant compute cluster that has interfaces into an API, and sort of like a JavaScript interface into it, that you can run geospatial analytics. And so it's a great, like I said, a great tool. Can't sing its praises enough. One of the aspects of it that make it less useful in certain contexts is that it is a little bit of a black box, right? The operations, the geospatial operations that you can do on it, the way that you can manipulate the data, are sort of whatever Google Earth Engine provides. If you wanted to run a PyTorch model against a large set of satellite imagery, that's like a lot more difficult. You can't really do that inside a Google Earth Engine. You have to like ship data out and ship data in, and getting data in and out of the system is a little tough, because it's like sort of a singular solution, and they
Right.
can optimize a lot based on that. So the approach we're taking is more a modular approach, leaning heavily on the open source ecosystems of tools, trying to make sure that the open source users are first class users that we're thinking of first, and that if people want to just use our data, we just have cloud optimized GeoTIFF, these flat file formats on blob storage. Go ahead and use it. You don't have to use any of the other stuff that we're building. But if you want to do spatiotemporal searches over it, we provide an API that's free access that allows you to do searches and get metadata about the data, so you don't have to actually read in the
Right.
petabytes. And then also providing the hub experience, which brings together that really rich open source ecosystem of Python tooling, including our tooling, and we're also building out other mechanisms to access this data. But the current focus is really on that Python data science. But yeah, considering the open source ecosystem sort of as our user experience, and trying to treat that as like the first class use case.
Yeah, that's fantastic. Tom, tell me if I have this right. I feel like my limited experience working with this is you've got these incredible amounts of data, but they're super huge. You all built these APIs that let you ask questions and filter it down into like I just want the map data for this, polygon or whatever. And then you provide a Jupyter notebook and the compute to do stuff on that result. Is that pretty good?
Yeah, that's pretty good. If you just think like the API is so crucial to have, and we'll get into what it's built on, but just for like the Python analogy here is like, imagine that you only had lists for your data structure. You didn't have dictionaries. And now you have to like traverse this entire list of files to figure out where is this one at, like in space on Earth, where is it at, or what time period is it covering? And the nice thing about the API is you're able to do very fast lookups over space and time with that to get down to your subset that you care about, and then bring it into memory ideally on machines that are in the same Azure region. Bring those data sets into memory using tools like Xarray or Pandas and Dask, things like that.
Yeah, very cool. So Rob, you mentioned the Postgres database. Do you like parse this data and generate the metadata and all that, and then store some of that information in the database so you get to it super quick, and then you've got the raw files as blob storage, something like that?
Yeah, for sure. I mean, that's as much metadata that you can capture and to describe the data so that you can kind of, do what Tom said and like ignore the stuff that you don't care about and just get to the area that you care about. We try to extract that and we do that according to a spec that is this really interesting, like community driven spec that one of the biggest complaints about dealing with satellite imagery and this Earth observation imagery is that it's kind of a mess. There's a lot of different scientific variables and sensor variables and things. So there's been a community effort over the past, I'd say 3 or 4 years to develop specifications that make this type of information machine readable. And so we've kind of bought fully into that and have processes to look at the data, extract the stack metadata, which is just a JSON schema specification with extensions, and then write that into Postgres. And one of the things that we, have been trying to do for like transparency and contribution to open source is a lot of that ETL code base, those the Python code that actually works over the files and extracts the metadata is open source in the Stack Utils GitHub organization. So we're trying to contribute to that sort of body of work of how to generate stack metadata for these different data types.
You want like the metadata for the exact same image that's coming from like the USGS public sector data set. You want the stack metadata to be identical for that, whether you're using our API or Google Earth Engines, who also provides a stack API. And so like we're working together on these kind of like shared core infrastructure libraries.
Yeah, nice. Well, let's dive into some of the data actually and talk a little bit about all these data sets. So a lot of data, as we said, over here. Maybe highlight some of the important data sets that you all have on offer.
So Sentinel-2 is our largest and is incredibly important. It's multispectral imagery, optical imagery that is 10 meter resolution. So it's the highest resolution. And when we talk about satellites, we often talk about what is the resolution that's captured, because something like Landsat, which we also have, Landsat 8, is 30 meter resolution. So once you get down to like street level, you can't really see, everything's blurry, right?
Each pixel represents 30 meters on the ground.
Exactly.
Right. Okay.
And so Sentinel is 10 meter. You get a lot clearer picture. You can track if you're doing sort of deforestation monitoring, for instance, like you can really track the edge of the deforestation a lot better with 10 meter imagery.
Right, or glaciers, you want to understand the boundary of it or something.
Exactly. And, it's still pretty low resolution compared to commercially available imagery. But as far as open data sets, it's high resolution. It's passively collected. I think the revisit rate is, I should have this offhand. I think it's 8 days. So you can really do like monitoring use cases with that. It generates petabytes and petabytes of data. So it's a lot to sort of work over. I mean, generating the stack metadata for that, it's like you got to fire up like 10,000 cores to kind of run through that. And you end up actually reaching the limits of how fast you can read and write from different services. But
oh my gosh.
Yeah, but it's a really great data set. A lot of work is being done against Sentinel-2.
So a lot of what I'm seeing when I'm reading through here is this annually, or this from 2000 to 2006, or like the one we were just speaking about, is since, from 2016. So this data is getting refreshed, and can I ask questions like, how did this polygon of map look 2 years ago versus last year versus today?
Totally. Yeah. And you can do that with the sort of API to say, okay, here's my polygon of interest. This is over my house or whatever. Fetch me all the images. But a lot of satellite imagery, most of it is clouds. It's just the Earth is covered in clouds. You're going to get a lot of clouds. So there's also metadata about the cloudiness. So you can say, okay, well, give me these images over time, but I want the scenes to be under 10% cloudy.
Right. I'm willing for it to not be exactly 365 days apart, but maybe 350 because I get a clear view if I do that. Something like this.
Exactly. And then you could make a little time lapse of how that area has changed over time. And in fact, I think there was somebody who actually demoed a time lapse of a similar type of time lapse, just grabbing the satellite imagery and turning it into a video over an area. I forget who exactly that was.
Yeah, very neat. Yeah, that one, the Sentinel, the large one, the revisit time is every 5 days. That's a lot of data.
Yep.
Yeah.
Yeah. It ends up a lot of data, a lot of clouds. A lot of clouds.
What about what about some of these other ones here? Got the DayMet, which is gridded estimates of weather parameters in North America. That's pretty interesting.
Yeah, so DayMet's actually an example of so a lot of our data is geospatial, like satellite imagery, or things that are derived from that, like elevation data sets, where you're using the imagery to figure out what's the elevation of the land, or things like land cover data sets. So if you scroll down just a tad, the land cover data set there, that's based off Sentinel, actually. And so this is saying, for every pixel in Sentinel, they took like a mosaic over a year. What is that pixel being used for? Is it water, trees, buildings, roads, things like that? So those are examples based off of satellite imagery or aerial photography. And then DayMet's an example of something that's like the output of a climate or a weather model. So these are typically higher dimensional. You're going to have things like, temperature, maximum, minimum temperature, water, pressure, vapor, all sorts of things that are stored in this really, big in-dimensional cube at various coordinates. So latitude, longitude, time, maybe height above surface. So those are stored typically in formats like ZAR, which is this cloud native, very friendly to object storage way of storing chunked in-dimensional arrays.
Is it like streaming friendly? You can stream part of it and seek into it, that kind of thing?
Exactly. And all the metadata is consolidated, so you can load in the whole data set in less than a few hundred milliseconds, but then access a specific subset very efficiently.
Sure. Yeah, very neat. Another one that's not directly based off of satellites is the high resolution electricity access, I'm guessing. And I guess you could sort of approximate it from lights, but is it? Do you think it's light off the satellite?
I think it is from Ron, do you know? Yeah. So I think it's
satellite.
from,
it's VIR satellite. Okay. So it is off of basically just studying light. Interesting.
Mm-hmm.
And we have a few more that are coming online shortly, which are kind of more tabular. So there's things like U.S. Census gives you like the polygons. So, the state of Iowa has these counties or census blocks, which are this shape. So giving you all those shapes, and it has this population, things like that. Things like GBIF has, which is, I think on there now, has occurrences of I think they're like observations of somebody spotted this animal or plant at this latitude, longitude at this time, things like that. So lots of different types of data.
Interesting. A mink was spotted running through the streets. Okay.
Yeah.
You have one for agriculture. That's pretty interesting. If you're doing something with agriculture and farming and trying to do ML against that.
Well, yeah, that's interesting because that's actually run by the National Agriculture. I forget the FDA. But that's actually aerial imagery, RGB, red, green, blue, and then also infrared aerial imagery that's collected about every 3 years. So that's an example of high resolution imagery that's more than I think it's 1 meter resolution.
Yeah, you can see the little trees and stuff right along
exactly.
the coastline. It's very, very accurate. Yeah.
Great data set specific to the US. So again, like Sentinel-2 is global in scope, but if you are doing things in the United States, NAPE is a great data set to use.
Yeah, you've got the USGS 3D elevation for topology. That's cool. Let's see. And then you have some additional data sets. What's the difference between the main ones and these additional ones? Why are they separated?
So we're catching up to where our Stack API has all of the data sets we host. But the AI for Earth program, which hosts all these data sets, has been going on since 2017. So there's plenty of data sets that they've been hosting that haven't yet made their way into the API. And that's, just because we're getting there. It's a bunch of work.
I see. So for these additional ones, maybe I could directly access them out of blob storage, but I can't ask API questions.
Exactly.
Okay.
And then another point, which is kind of interesting, talking back to the tabular data, is that some of these data formats aren't quite. I mean, rasters and imagery fits really nicely in Stack, and we know how to do spatiotemporal queries over them. But some of these data formats, they're not as mature as maybe the raster data format, or it's not as clear how to host them in a cloud optimized format and then host them in a spatiotemporal API. So we're actually having to do work to say, okay, what are the standards? Is it like GeoParquet, or what are the formats that we're going to be using in hosting these data sets? And then how do we actually index the metadata through the API? So there's a lot of sort of data format and specification, metadata specification work before we can actually host all of these in the API.
Yeah, really nice. A lot of good data here, and quite large. Let's talk about the ETL for just a minute, because you threw out some crazy numbers there. We're looking at the Sentinel-2 data, and it gets refreshed every 5 days, and it's the Earth. Talk us through what has to happen there.
Yeah, so for the Sentinel, it's actually daily. It's passive satellite collection. So the satellites are just always monitoring, always grabbing new imagery. And so that comes off to ground stations through the European Space Agency. And then we have some partners who are taking that, converting it to the cloud optimized GeoTIFF format, putting it on blob storage, at which point we run our ingest pipelines, look for new imagery, extract the Stack metadata, and insert that into the database. And we just have that running in an Azure service called Azure Batch, which allows us to run parallel tasks on clusters that can auto scale. So if we're doing an ingest of a data set for the first time, there's going to be a lot of files to process, and we can scale that up. And it runs Docker containers. So we just have a project that defines the Docker commands that can run, and then we can submit tasks for chunks of the files that we are processing. That creates the Stack items, and then another separate process actually takes the Stack items and inserts it into the database.
That's cool. So it's a little bit like data driven rather than a little bit like Azure Functions or AWS Lambda, but processing. We just got to get all this data and just work through it kind of at scale. Interesting.
Yeah, for sure. Right now, it's a little bit. We're still building the plane as we're flying it, but the next iteration is actually going to be a lot more reactive and based on another Azure service called Event Grid, where you can get notifications of new blobs going into storage and then put messages into queues that can then turn into these Azure Batch tasks that are run.
Right. I see. So you just get something that drops it in the blob storage, and it kicks off everything from there, and you don't have to worry about it.
Yep.
And then we publish those to our users, saying, "Hey, this is ready now." Or if they subscribe to that to that Event Grid topic.
Oh, that's cool. There's a way to get notified of refreshes and things like that.
Not yet. We're hoping to get that end of year, but yeah, the idea is that we would have basically a live feed of new imagery. I mean, what I would really like to see, just for myself, for my own interest, is like to be able to have my areas of interest and then just go to a page that shows like almost an Instagram feed of Sentinel images over that area. It's like, oh, this new one, it's not cloudy. Look at that one. You know, it's something I'm monitoring. But yeah, generally we'll be publishing new stack items so that if you're running AI models off of the imagery as it comes in, you can do that processing based off of events.
Yeah, that'd be cool. Like, I'm only interested in Greenland. I don't care if you've updated Arizona or not. Just tell me if Greenland has changed, then I'm going to rerun my model on it or something.
Right.
Cool. All right. Let's see. So that's the data part, data catalog. And then we have the API and the hub, which I want to get to, but I kind of want to just sort of put some perspective on what people have been doing with this, some of your partner stuff under the applications thing. So Tom, which ones do you think we should highlight from those that are interesting?
I think we kind of talked about the land cover data set. So we worked with Impact Observatory and Esri to do that. And so like they were we had some tips about how to use Azure Batch, because that's a very big Azure Batch job to generate that land cover map. So pulling down the Sentinel data that we're hosting and then running their model over it. So that was a fun data set to see come together and then use now. The Carbon Plan, carbon monitoring risk assessment application. That's like a really cool. So it's a cool like JavaScript application that you can view risks on. So these companies are buying like carbon offsets that are trees that are planted to offset carbon. But there's a problem that we know about now is like the wildfires are burning down those some of those forests. And so
it doesn't help if you planted a bunch of trees to offset your carbon if they go up in smoke, right?
Yeah. So Carbon Plan did a bunch of research, first of all, on essentially a hub. They did the research before our hub existed, but we were working with these community members and they have a very similar setup to what we have now, to do the research, to train the models and all of that that goes into this visualization here of how likely, what are the different risks for each plot of land in the US. So that was a great collaboration there.
And then one of the things I was wondering when I was looking at these is you all are hosting this large amounts of data and you're offering compute to study them. How does something like Carbon Plan take that data and build this seemingly independent website? Does that run directly on that data, or do they like export some stuff and then run it on their side, or what's the story?
Yep. So this was they would have been doing all like the heavy duty compute ahead of time to train the models and everything to gather the statistics necessary to power this. So then at that point, it's just a static JavaScript application just running in your browser now.
Oh, interesting.
Yeah, and I think that's a good point, because it's running against our data, but it's running in their own infrastructure. Right. So it's sort of on the planetary computer, but it's like really in this case, like using the planetary computer data sets in sort of, a production setting, that an infrastructure that they own, which is a use case we really want to support. If they need to use search in order to find the images that they need, they can use our Stack APIs. But really, it's like just an application running in Azure. That, in certain cases with our grants program, we'll end up supporting and sponsoring Azure subscriptions to run this type of infrastructure. But at the end of the day, it's really just applications running in the cloud.
Right. It's just better if that it's in Azure, that it's nearby, but they could run it anywhere technically, right? And just get signed blob storage access or whatever.
Mm-hmm.
Yeah, we'll throttle access at a certain point if you're trying to egress too much. But
I can imagine. Yeah, very cool. I can come over here and zoom in on Portland, and it looks like we're in a decent bit of greenness still. It does rain up here a lot. Same for Seattle.
Yeah.
Yeah, quite cool. You talked about this grant program. What's the story with that? People out there listening, they're like, I want to get into working with this data and building things. Grant might sound good to them. What is that?
Awesome. Yeah. Look up AI for Earth grants. We have rounds of supporting folks that are doing environmental sustainability work, and there's a sort of a range of grant rewards. The lowest level is like giving Azure credits. Being able to sponsor an account or sponsor resources for applications that are being developed or research that's being done for environmental sustainability. And we have folks running the grants program and go take the applications and there's different classes that we have and summits for each of the classes. And then there's more involved grants and larger grants as usually as people sort of show progress, we actually can end up bringing additional resources or paid projects to accomplish specific goals. But yeah, if anybody's out there and they're doing work in environmental sustainability that could benefit from the cloud, we'd love to work with you.
Cool. And maybe just to clarify, so there's the grants are great for like if you have like a complex deployment that's using a ton of Azure services and you want to like integrate this all together and use the Planetary Computer data, then the grants are a great approach. If you're just like an individual researcher or a team of researchers or whoever who wants to use this data, the data's there, it's publicly accessible. And if you need a place to compute from that's in Azure, so close to the data, and you don't already have an Azure subscription, then you can sign up for a Planetary Computer account. And so like that's a way lower bar of barrier to entry. There is you just sign up for an account, you get approved by us, and then you're off to the races.
That's a great point. If you think you need a grant to use the cloud, try using the Planetary Computer first, because you might not.
Yeah, very good. So what's the business model around this? Is there going to be a fee for it? Is there some free level? Is it always free but restricted how you can use it?
So
right now it's in like a private beta, right? I can come down and request access to it.
Yeah, it's a preview. We're still like gating access by requiring requests, and there's a larger number of requests we're approving over time. We're still coming up with the eventual, final sort of target. Most likely, it will be some sort of limits around what you can do as far as compute, as far as like data storage once we have features around that. And with clear offboarding of like if you're an enterprise organization that wants to utilize this technology, there should be paid services that allow you to just as easily do it as you're doing on the Planetary Computer. But if you're a doing low usage use cases, or if your use cases is super environmental sustainability focused, and you apply for a grant, we could end up you're still using a paid service, but we're covering those costs through our grants program. So we're still figuring that out as far as, we're not, I don't see this as something that we're, trying to turn into a paid service necessarily. I think that there's a number of, enterprise level services that could end up, looking a lot like the Planetary Computer, but really we want to continue to support uses, particularly for environmental sustainability use cases, through this avenue.
Yeah. One of the nice things about our overall approach is, since we're so invested in the open source side of things, is if we're, you might have requested an account a while ago and we're like very slowly going through them because there's just like so much to do. But if we're too slow approving your account, then you can replicate the hub in your own Azure subscription. So if we're blocking you, or if your needs are just like so vastly beyond what we can provide within this one subscription, then you can go ahead and do your own setup on Azure and get access to our data from your own subscription.
Right, because the blob storage is public, right?
Exactly. Yep.
Okay. Yeah, very nice. All right, maybe the next two things to talk about are the API and the hub, but I think maybe those would be good to see together. What do you think?
Yeah,
All right.
definitely.
I think I'll let you talk us through some scenarios here, Tom.
Cool. Yeah. So I'm in this case, I've logged into the hub here. So I've this is a yeah.
Before you go further, there's a choice you get when you go there. You've got an account and you click start my notebook up.
Yeah.
It's actually going to fire up a machine, and it gives you 4 choices, right? Python with 4 cores and 32 gigs of memory, and a Pangeo notebook. It gives you R with 8 cores and R geospatial and GPU PyTorch, as well as QGIS, which I don't really know what that is. Maybe tell us about getting started. QGIS.
Yeah. So this is a Jupyter Hub deployment. So Jupyter Hub's this really nice project. I think it came out of UC Berkeley when they were kind of teaching classes, data science courses to like thousands of students at once. And even with like Conda or whatever, you don't want to be trying to manage 1,000 students' Conda installations or whatever. So that's just a nightmare. So they had this kind of cloud-based setup where you just log in with your credentials or whatever, and you get access to a compute environment to do your homework in that case, or do your geospatial data analysis in this case. And so this kind of, you mentioned Pangeo, this is this ecosystem of geophysicists, geoscientists who are trying to do scalable geoscience on the cloud that Anaconda was involved with. And so they kind of pioneered this concept of a Jupyter Hub deployment on Kubernetes that's tied to Dask. So you can easily get a single node compute environment here, in this case using the Python environment, or multiple nodes, a cluster of machines to do your analysis using Dask and Dask Gateway. Nice. But yeah, it's just a Kubernetes based computing environment.
That's cool. And I noticed right away the Dask integration, which is good for like this massive amounts of data, right? Because it allows you to scale across machines, or more stream data where you don't have enough to store it in memory and things like that.
Yep, exactly. So this is a great thing that we get for Python. So Dask is Python specific. We do have the other environments like R for if you're doing geospatial in R, which there's a lot of really great libraries there. That's an option. That is unfortunately single node. There's not really a Dask equivalent there, but there's some cool stuff that's being worked on, like multi-dplyr and things like that. Nice. Anyway. And then there's
if people haven't, cool. If people haven't seen Dask running in Jupyter Notebook, there's the whole cluster visualization and the sort of progress computation stuff is super neat to see it go.
Yeah. So it's when you're doing these distributed computations, it's really key to have an understanding of what your cluster's up to. It's just crucial to be able to have that information there.
And in the example code that you've got there, the cloudless Mosaic Sentinel 2 notebook, it just has the like basic create me a cluster in Dask, get the client, create 4 up to 4 to 24 workers, and then off it goes, right?
Yeah, exactly.
So what is the limits, and how does that work, right? As part of getting an account on there, you get access to this cluster?
Yep. So this is the first thing that we talked about today that does require an account. So the hub requires an account, but accessing like the Stack API, which we'll see in a second, and even downloading the data does not require an account. You can just do that anonymously. Okay. And in this case, I think the limit's like 1,000 cores, something like that, or some memory limit as well. So that's the limit that you'll run into there. So you can get quite a bit out of this. Yeah,
setup. That's real computing right there, and that's a lot.
Definitely.
A lot of processing power.
And in this case, we're using Dask's adaptive mode. So we're saying, right now there's nothing to do. It's just sitting around idly. So I have 3 or 4 workers. But once I start to actually do a computation that's using Dask, it'll automatically scale up in the background, which is a neat feature of Dask. Yeah, and so the basic computation, the problem that we're trying to do here is we have some area of interest, which I think is over Redmond, Washington, Microsoft headquarters, which we're defining as this bounding
An exact
box.
square, yeah.
Yeah. So
heck.
some sort of, I think that's a polygon, a square polygon.
Yeah.
But anyway, we draw that out, and then we say, okay, give me all of the Sentinel-2 items that cover that area. So again, back to what we were talking about at the start, is like if you just had files in blob storage, that'd be extremely difficult to do. But thanks to this nice Stack API, which we can connect to here at planetarycomputer.microsoft.com, we're able to quickly say, hey, give me all the images from 2016 to 2020 from Sentinel that intersect with our area of interest here. And we're even throwing in a query here saying, hey, I only want scenes where the cloud cover is less than 25%, according to the metadata.
So very likely summer in Seattle, because the winter, not so much.
Much fewer. Yeah, much fewer. So, quickly within a second or two, we get back the 138 scenes items out of the, I don't know how many there are in total, but like hundreds of thousands, millions of individual Stack items that
20 million?
20 million, okay. That comprise Sentinel-2. So we're quickly able to filter that down. Next up, we have a bit of signing. So this is that bit that we talked about where you can do all this anonymously, but in order to actually access the data, we have you sign the items, which basically appends this little token to the URLs. And then at that point, they can be opened up by any geospatial program like QGIS or
it converts a private blob storage URL to a temporary public one.
Yep, exactly.
Okay.
Exactly.
So you do that,
One of the great, I don't know, it's just like this kind of incidental happenstance that Stack and Dask actually pair extremely nicely. If you think about Dask, the way it operates is it's all about lazily constructing a task graph of computations. And then at the end of your whatever you're doing, computing that all at once. That just gives really nice rooms for optimizations and maximizing parallelization wherever possible. The thing about like geospatial is if you didn't have Stack, you'd have to open up these files to understand like where on Earth is it, like what latitude, longitude does it cover? Or what
you have
time
to open up all 20
cover.
million files and then look and see what its metadata says in it, right?
Yeah.
Okay.
And in this case, we have like 138 times 3 files. So 600, 450, 600 items, files here. Opening each one of those takes a few, maybe 200, 400, 500 milliseconds. So it's not awful, but it's like too slow to really do interactively on any scale of any large number of Stack items. So that's where Stack's great. It has all the metadata. So we know that this TIFF file, this cloud optimized GeoTIFF file that contains the actual data, we know exactly where it is on Earth, what latitude, longitude it covers, what time period it covers, what asset it actually represents, wavelength. So we're able to very quickly stack these together into this X-ray data array that's, in this case, it's fairly small since we've chopped it down. If we leave out the filtering, it'd be much, much larger because these are really large scenes. But anyway, we're able to really quickly generate these data arrays. And then using our Dask cluster, we can actually persist those in distributed memory on all of the workers on our cluster. So that's like
very cool.
Very easy. Like it's like, a few lines of code, a single function call, but it like represents years of effort to build up these Stack specification and all the metadata and then the integration into Dask. So it's just a fantastic result that we have.
Yeah, and it's super cool once you just call data.persist on the Dask array, you could just see in the dashboard of Dask like all these clusters firing up and all this data getting processed, and very neat.
Yep, exactly. So in this case, since we have that adaptive mode, we'll see additional workers come online here. As we start to stress the cluster, it's saying, oh, I've got a bunch of unfinished tasks. I should bring online some more workers. And that'll take, either a few seconds if there's empty space on our cluster or a bit longer. And then
Yeah, I feel like with this, if it just sat there and said it's going to take 2 minutes and just spun with a little star, the Jupiter star, that would be boring.
Yeah,
but it has this
that
cool
would be-
animated little dashboard. Like, I'm gonna just watch it go. Look at it go.
Yeah.
It's kind of like defragging your hard drive in the old days.
Yep.
It's just you watch these little bars go across. It's very bizarre, bizarrely satisfying.
Yep, I will definitely just spend some time sitting here watching it. Ostensibly like monitoring. There's like a lot of communication here. There shouldn't be, but really, I'm just watching the lines move.
While the thing is working, let me take a question from the live stream. Simparia asks, can users bring their own data to this sort of processing, or because you've got the data sets that you have, is there a way to bring other research data over?
Yeah, so the answer now is like yes, but you kind of have to do a lot of effort to get it there. Like, so your own data, you probably maybe you do have like your own Stack API and database setup and all of that, but that's publicly accessible or you have a token for. So most users don't already have that. So you can't. There's this real divide between the data sets that we provide with our nice Stack API and like your own custom data set that might be a pile of files and blob storage, and you could access it that way certainly, but there's kind of a divide there. So that is definitely something that we're interested in improving, is making user data sets like that are private to you feel as nice to work with as our own public data sets.
Yeah, another thing that I saw when I was looking through, it said under the data sets available, it says, or if you have your own data and you'd like to contribute, contact us. And that's a slightly different question than they were just asking. That's the one question was, well, I have my own data, I want to use it. This is like how I work at a university or something. I've got all this data. I want to make it available to the world. What's the story with that?
Rob, do you want to do that one?
Yeah, so we have a backlog of data sets that we're onboarding onto Azure Blob Storage and then importing into the API. Still working through that backlog, but always on the lookout for good data sets that have real use cases in environmental sustainability. If there's a group that's doing some research or building applications that have environmental sustainability impact, and they need a data set, that certainly bumps it up on our list. So yeah, I would love to hear from anybody that has data sets that you're looking to expose publicly, hosts on the Planetary Computer for anybody to use. And need a place to host it. Yeah,
very cool. All right, Tom, your graph stopped moving around. Looks like it might be done.
Yeah, so we spent quite a while loading up the data, and then that's like just how it goes. You spend a bunch of time loading up data, and then once it's in memory, computations tend to be pretty quick. So in this case, we're taking a median over time. So
is this the median of the image? What is it? What is that a median of?
Yeah,
so I know what that means for like a list of numbers. I'm not sure what it means for an image.
Yeah, so this is a median over time. So our stack here, our data array is a 4-dimensional array, and the dimensions are time, first of all. So we had like 138 time slices, wavelength. So these red, green, blue, near infrared. Sentinel captures like 10 or 12 wavelengths, and then latitude and longitude. So we took the median over time, and the idea here is that like stuff like roads and mountains and forests tend not to move over time. They're static relatively compared to something like clouds. So again, clouds are always a problem. And once you take the median over time, you kind of get like the average image over this entire time period, which turns out to be an image that doesn't have too many clouds in it.
Yeah, it might have no clouds because if you kind of averaged them out across all of them, because you already filtered it down pretty low. Yeah.
Yeah, so now we can see a picture of the Seattle area where it's a cloud-free composite or a cloudless mosaic.
Beautiful. Looks like you got, maybe that's, what's that, Lake Washington, and you got Rainier there and all sorts of good stuff. Yeah.
Yeah, I'm sure. I actually do not know the geography of that well, but I have been looking at lots of pictures. We tend to use this as our example area a lot. So
yeah, super cool.
Anyway, and one nice thing here is like, so we're again investing heavily in open source, investing in building off of open source. So we have like all the power of Xarray to use. X-ray is this like very general purpose n-dimensional array computing library. It kind of combines the best of NumPy and pandas. In this case, we can do something like group by. So if you're familiar with pandas, you're familiar with group bys. We can group by time dot month. So I want to do like a monthly mosaic. Maybe I don't want to combine images from January, which might have snow in them, with images from July, which wouldn't have as much. So I can do a.
So you get like 12 different images or something like that. Here's what it kind of averaged out to be in February.
Exactly. And so now we have a stack of images, 12 of them, and we can go ahead and it representing a median. So we have multiple years, and we group all of the ones from January together and take the median of those. And then we get a nice little group of cloud-free mosaics here, one for each month.
Yeah, and sure enough, there's a little less snow around Rainier in the summer than in the winter, as you would Cascades.
Yep, definitely. So that's like a fun little introductory example to what the hub gives you. It gets you the single node environment, which that alone is quite a bit. You don't have to mess with fighting to get like the right set of libraries installed, which can be especially challenging when you're interfacing with like these C and C++ libraries like GDAL. So that environment is all set up, mostly compatible, should all work for you on a single node. And then if you do have these larger computations, we saw it took a decent while to load the data, even with these fast interop between the storage machines and the compute machines in the same Azure region. But you can scale that out on enough machines that your computations complete in a reasonable amount of time.
Yeah. And because of the animations, you don't even mind. It's super cool. So you use the API to really narrow it down from 20 million to like 150 or 138 images, and then keep running on it. So one thing that I was wondering when I was looking at this is, what libraries come included that I can import, and which ones, if there's something that's not there, maybe I really want to use HTTPX and you only have requests or whatever. Like, is there a way to get additional libraries and packages and stuff in there?
Yeah. So we do have a focus on geospatial, so that's like we'll have most of that there already. So Xarray, Dask, Rasterio, and all those things. But if there is something there, our container. So these are all Docker images built from Conda environments, and that's all comes from this repository, Microsoft /Planetary Computer containers. So if you just, you want HTTPX, you add it to the environment.yaml, and we'll get a new image built, and then available from the Planetary Computer. And so these are public images. They're just on the Microsoft Container Registry. So if you want to, we use our image, like you don't want to fight with getting a compatible version of say PyTorch and libjpeg. Not that I was doing that recently, but if you want to avoid that pain, then you can just use our images locally, like from your laptop. And you can even like connect to our Dask gateway using our images from your local laptop and do like some really fun setups there.
Yeah, I see. Because most of the work would be happening in the clusters, the Dask clusters, not locally anyway.
Yeah, so all the compute happens there, and then you bring back this little image that's your plot, your result.
Okay, yeah, very cool. So how do I get mine in here? Like I see the containers, and I see you have the last commit here.
Yeah, but, so there's one per. Right now, honestly, the easiest way is to send me, open up an issue, and I'll take care of it for you. Just because I haven't got this continuous deployment quite working out, but there's an environment, .yaml file there.
So you go see. Yeah, there's quite a few packages in here already.
Yep, and those are just the ones we explicitly ask for, and then all their dependencies get pulled into a lock file and then built into a Docker images. And so this is building off a project from Pangeo, that group of geo scientists that I mentioned earlier, who have been struggling with this problem for several years now. So they have a really nice Dockerized setup, and we're just building off that base image.
Cool. Yeah, based on the Pangeo container. Very cool. Samapuria asks, how long is the temporary URL active for, the signed URL, the blob storage?
So that actually depends on whether or not you're authenticated. We have some controls to say, the Planetary Computer Hub requires access, but also you get an API token, which gives you a little bit longer lasting tokens. But I forget what the actual current expiries are. If you use the Planetary Computer Python library, you just pip install planetary underscore computer and use that .sign method. It will actually request a token, and then as the token is going to expire, it requests a new token. So it reads this token and caches it. But it should be long enough for actually pulling down the data files that we have available, right? Because we're working against smaller cloud optimized formats. There aren't these 100 gig files that you should have to pull down and need a single SAS token to last for a really long time. So you can re-request if you need a new one as it expires. And like I said, that library actually takes care of the logic for you there.
Oh, that's cool. Yeah, very nice. All right, guys, really good work with this. And it seems like it's early days. It seems like it's getting started. There's probably going to be a lot more going on with this.
Yeah,
for sure.
It's really fun.
I'm going to go out on a limb and make a big prediction that understanding the climate and climate change is going to be more important, not less important in the future. So I suspect that's also going to grow some interest.
It might, and the new report IPCC is making some heavy predictions, and within the decade, we might reach plus 1.5 Celsius, and we're already in it. We're already feeling the effects, and this is the data about our Earth, and it's going to become more and more important as we mitigate and adapt to these effects. So yeah, I agree. I think that's a good prediction.
Yeah, if we thanks. If we are going to plan our way out of it and plan for the future and science our way out of it, we're going to need stuff like this. So well done.
Thank you.
All right, I think we're about out of time, so let me ask you both the final two questions here. If you're going to write some Python code, what editor do you use? Rob?
VS Code.
I suspect I could guess that, but yeah.
Yeah, actually, I was a big Emacs user, and then when I got this job, switched over to VS Code because it just integrated better with Windows, and then really got into the PyLance and the typing system. Doing type annotations and basically having a compiler for the Python code. Like really a change, instead of having all of the types in my head and having to worry about all that, actually having the type hinting was something I wasn't doing a year ago. And now it's drastically improved my development experience.
It's a huge difference. Yeah. And I'm all about that as well. People talk about the types being super important for things like MyPy and other stuff. And, in a lot of cases it can be, but to me, the primary use case is when I hit dot after a thing, I want it to tell me what I can do. And if I have to go to the documentation, then it's kind of like something is failing. I shouldn't need documentation. I should be able to just, auto-complete my way through the world mostly.
Totally. And I come from I was a Scala developer for, about 6 years. So I was used to a very heavily typed system. And kind of got away with it from Python. I was like, what? I like that there's not types, but I feel like the Python ecosystem is really hitting that sweet spot of introducing enough typing where it's really great.
And then the inference flies along for the rest of the program. Yeah,
totally.
Yeah. All right, Tom, how about you?
VS Code as well for most stuff, and then Emacs for Magit, the Git client, and then a bit of Vim every now and then.
Right on. Very cool. All right. Then the other question is for either of you, if there's a cool, notable PyPI or Conda package that you're like, oh, I came across this. It was amazing. People should know about it. Any ideas?
How are you going?
Sure. I'll go with Seaborn. It's a plotting library from Michael Wascom, built on top of Matplotlib. It's just really great for exploratory data analysis. It's just, easily create these great visualizations for mostly tabular data sets, but not exclusively.
Oh, that's interesting. I know Seaborn, I knew Matplotlib. I didn't realize that Seaborn was let's make Matplotlib easier.
Yeah, essentially for this very specific use case, Matplotlib is extremely flexible, but there's a lot of boilerplate, and Seaborn just wraps that all up nicely.
Yeah, super cool. All right. Well, thank you so much for being here. Final call to action. People want to get started with Microsoft Planetary Computer. Maybe they've got some climate research. What do they do?
planetarycomputer.microsoft.com. That'll get you anywhere you need to go. And then if you want an account, then it's /account/request, I believe.
Yeah, there's a big request access
Yep.
right at the top. So you can click that. Awesome.
Yeah, exactly.
All right, Rob, Tom, thank you for being here. And thanks for all the good work.
Thanks
Awesome.
for having us.
Thanks so
This is great.
Yep. Bye.
Cheers.
See ya.